Hello everyone. Today we are going to solve a 2D transient heat conduction problem with heat flux boundary conditions, also known as Newman boundary conditions in Cartesian coordinates using FTCS or forward time center space finite difference method. Our objectives are to present a simple 2D transient heat conduction problem with no heat generation term involved. The boundary conditions considered are Newman boundary conditions. We consider constant heat flux at the boundaries. We will discretize the domain into a 3 by 3 grid. We'll consider a single time step and solve the problem using forward time centered space or FTCS finite difference method. We'll vary the grid spacings and time steps and resolve the problem and obtain temperatures inside the domain. Our domain is a square copper plate which is 0.3 meters long and 0.3 meters wide. The initial temperature of the copper plate is represented as Tn, which is equal to 0 is equals to 20 degrees Celsius. The material properties are represented by alpha and K. Here alpha is the thermal diffusivity and is equal to 1 e to the negative 4 meter square per second. K is the thermal conductivity of the material, which is equal to 386 watts per meter Kelvin. Q1y, Q2x, Q3y, and Q4x are all the heat flux at the four sides of the copper plate. The sign convention is chosen to represent heat is flowing out of the domain in all four sides. The x and y coordinate directions are shown at the top left hand side. The general heat conduction equation in 3D Cartesian coordinates is given as dou square T over dou x square plus dou square T over dou y square plus dou square T over dou z square plus G over K equals 1 over alpha times dou T over dou T. Here T represents the temperature inside the domain and is a function of the spatial coordinates x, y, z, and T, where the lowercase t represents time in seconds. Alpha is the material property called thermal diffusivity and is given in meters squared per second. Alpha equals K over rho C, where K is the thermal conductivity of the material in watts per meter Kelvin. Rho is the density of the material in kilograms per meter cube. C is the specific heat capacity of the material in joules per kilogram Kelvin. And G is the volumetric rate of internal heat generation in watts per meter cube. We assume that the material thermal conductivity is homogeneous and isotropic. Accordingly, K is uniform over the entire domain. For 2D transient heat conduction with no heat generation, equation 1 reduces to a simpler form. We assume that the temperature does not vary significantly along the z direction when compared with x and y directions. In other words, we assume that along the z direction, both sides of the plate is insulated. The heat generation term G equals 0. Accordingly, we get dou square T over dou x square plus dou square T over dou y square equals 1 over alpha times dou T over dou T. And T is a function of x, y, and T. Rearranging equation 2, we get dou T over dou T equals alpha times dou square T over dou x square plus dou square T over dou y square. T is equal to T of x comma y comma T and T is greater than 0. The initial condition IC is given as T at x comma y comma T equals 0 equals Tn. The boundary conditions are at the top end Q1y equals 38,600 watts per meter square, where Q1y is the heat flux at the top side. Likewise, at the right side, at the bottom side and at the left side, Q2x equals Q3y equals Q4x. They're all the heat fluxes at these three sites, and they are given as 38,600 watts per meter square. As mentioned before, the sign convention is chosen to represent that heat is flowing out of the domain in all four sites. L is the length of the domain in x direction and W the length of the domain in y direction. To obtain the temperature distribution T, we need to solve the above PDE. We'll utilize finite difference method to solve the above PDE. To do so, we need to replace the partial derivatives with finite difference approximations. We'll replace the time derivative with first order forward difference and the space derivatives with second order centered difference approximations. Accordingly, we get Ti, j n plus 1 minus Ti, j n over delta T equals alpha times Ti minus 1, j n minus 2 times Ti, j n plus Ti plus 1, j n over delta x square plus Ti, j minus 1 n minus 2 times Ti, j n plus Ti, j plus 1 n over delta y square. For simplicity, let delta x equals delta y. Accordingly, we get Tij n plus 1 equals Tij n plus alpha delta T over delta x square times Ti minus 1, j n plus Ti plus 1, j n minus 4 times Ti, j n plus Ti, j minus 1 n plus Ti, j plus 1 n. Let d equals alpha times delta T over delta x square, where d is the diffusion number. We then get Ti, j n plus 1 equals Ti, j n plus d times Ti minus 1, j n plus Ti plus 1, j n minus 4 times Ti, j n plus Ti, j minus 1 n plus Ti, j plus 1 n. Equation 5 is the finite difference approximation of the original equation we were trying to solve. Here I represents the node location along the x direction, j represents the node location along the y direction, and n represents the time step. The above approximation is called forward time center space or FTCS method. This is an explicit method. Hence, temperatures Tij's at future times n plus 1 can be directly obtained based on Tij's at present times, as shown in equation 5. Explicit methods are conditionally stable. The stability criteria for this problem is given as D should be lesser than or equal to 0.25 for 2D problems. Also, time step delta T needs to be small based on the accuracy desired. The error is of the order of delta T plus of the order of delta x square plus of the order of delta y square. Now let us discretize the 2D domain into a 3x3 grid equally spaced as shown below. We have 16 nodes in total. This includes the interior nodes as well as the boundary nodes. Let us apply equation 5 on the 16 nodes. Accordingly, we get for the first node T11 n plus 1 equals T1, 1 n plus d times T0, 1 n plus T2, 1 n minus 4 times T1, 1 n plus T1, 0 n plus T1, 2 n. Likewise, we can get similar equations for the remaining nodes, where I equals 2, j equals 1, and so on. Let's note that temperatures at boundary nodes are not known in this case, but we do know that the heat flux at boundary nodes. According to Fourier's law of heat conduction, Q equals minus k times dt over dx, where qx is the heat flux given in watts per meter square. K is again the thermal conductivity of the material in watts per meter Kelvin. Rearranging the above equation, we get dt over dx equals minus qx over k. Here dt over dx is the temperature gradient given in Kelvin per meter. Let us apply the constant flux boundary conditions at the top end. Accordingly, we get dt over dy at y equals 0 equals minus q1y over k Kelvin per meter. We now approximate the first order space derivative using center difference approximation. We then get ti, j plus 1 minus ti, j minus 1 over 2 times delta y at y equals 0 equals minus q1y over k. At I equals 1, 2, 3, 4 and j equals 1, we have ti, 2 minus ti, 0 over 2 times delta y equals minus q1y over k. Rearranging ti, 2 minus ti, 0 equals minus 2 times delta y times q1y over k, or ti, 0 equals ti, 2 plus 2 times delta y plus q1y over k. Here ti, 0 are the hypothetical nodes just outside the boundary location at the top side. Similarly, at the right hand side, we can get the following equation: t5, j equals t3, j minus 2 times delta x times q2x over k. Here t5, j represents the hypothetical boundary nodes, hypothetical nodes just outside the boundary at the right hand side. Likewise, we can get similar equations for the bottom end or bottom side as well as the left hand side. So we can now substitute equations 6, 7, 8 and 9 into the previous set of equations. Accordingly, we get for the node 1, 1, t1, 1 n plus 1 equals t1, 1 n plus d times t2, 1 n plus t2, 1 n plus 2 times delta x times q4x over k minus 4 times t1, 1 n plus t1, 2 n plus 2 times delta y times qy over k plus t1, 2 n, and so on for all the 16 nodes. You can rearrange these equations further as shown here. For the first time step, let n equal 0. We then get t1, 1 equals t1, 1 0 plus d times 2 times t1, 1 0 minus 4 times t1, 1 0 plus 2 times t1, 2 0 plus 2 times delta y q1y over k plus 2 times delta x times q4x over k, and so on for the remaining nodes. Let delta t equals 0.1 second. Delta x equals L over nx, or 0.3 over 3 equals 0.1 meter. And delta y equals delta x equals 0.1 meter. The heat fluxes Q1y equals Q2x equals 38,600 and Q3y equals Q4x equals negative 38,600. The thermal conductivity KT equals 386 watts per meter Kelvin. Accordingly, we can get Q1y over KT equals Q2x over KT equals 38,600 over 386 equals 100 Kelvin per meter, and this is the temperature gradient at these two surfaces, at these two sides. The diffusion number D equals alpha times delta T over delta X squared, which is equal to 0.001, which is lesser than 0.25. So we meet the stability criteria. Let us now substitute the initial temperatures, the diffusion number D, heat fluxes, the thermal conductivity, grid spacing values delta X and delta Y into the previous set of equations. Accordingly, we can solve the temperature at these 16 nodes for the first time step. And is represented in the sketch. Likewise, we can find the temperatures at these interior as well as the boundary nodes for the next time step by choosing n equals 1 and so on. We presented some graphical results using MATLAB. For this case, we're going to present. So using MATLAB or other software, we can develop a course for a general case where the number of grid spacings and time steps can be varied as desired, and we can obtain solutions accordingly. We'll now go back to MATLAB. All the various parameters here for this 2D heat conduction problem with heat flux boundary conditions are given here. Alpha equals 1 e to the negative 4. Thermal conductivity here is represented as KT equals 386 watts per meter Kelvin. The total time is considered as 1 second, and delta T equals T over 10 equals 0.1 second. X length is 0.3, delta X equals X length over 3, which is equal to 0.1 meters. The heat fluxes Q1y, Q2x, Q3y, Q4x are given as 38,600 with appropriate signs, and the thermal gradient F1y, F2x, F3y, F4x are given as shown here. For example, for F1y, which is equal to Q1y over KT and so on. The initial temperature is given as T in, which is equal to 20 degrees Celsius. We'll run this program now. Let's look at the graphical portion here. So the left hand side of this screen at the top end shows the initial condition. The bottom at the left hand side is the final condition, and we just saw the animation at the right hand side. So for the first time step, here 1 represents the initial time step. The temperature at all 16 nodes are given as 20 degrees Celsius. For the first time step, we have the temperature distribution shown here, and this should match the values we calculated. For example, 19.96 at the corners and 19.98 degrees Celsius at the sides, and 20 degrees Celsius at the interior nodes. And I think we calculated the same values in MATLAB. So now we will basically change the time steps, the total time, for example. Let's change it to 100 seconds. And we'll change delta t as well to say 1 second. And delta x, let's change that to 0.3 into 10 grid spacings. And we'll save this and resolve this problem. So the initial conditions again are at the top left hand side, and the final conditions are at the bottom left hand side. On the right side of the screen we see the animation, and since we get the total time as 100 seconds, this is going to run until we hit t equals 100 seconds. You can see that the copper plate is cooling with time and the temperatures are dropping. So now let's go back to our MATLAB, to our PowerPoint. To summarize, in this video we presented a 2D transient heat conduction problem in Cartesian coordinates. The boundary conditions considered are Newman boundary conditions, that is, we considered constant flux at the boundaries. The initial temperature in the domain is known. Using FTCS finite difference method, we discretized our domain. We obtained temperatures inside the domain at various times and solved the problem. We varied the grid spacings and time steps and resolved the problem and presented the results using MATLAB. In future videos, we can explore more challenging problems. If you have any comments or questions, please post it. Thanks for watching.